Welcome. In this video I'll introduce a fixed boundary solver for a Grach-Farnoff equation. So this is one that's available publicly. It's called FreeGS. It's really intended for free boundary calculations, and I'll show you how to do that later in a different video. But here we can try and use it for simple fixed boundary calculations in rectangular domains. So there are obviously more sophisticated codes, things like Helena that were covered in the previous talks. These use finite element methods and curved geometries. But hopefully this code is simple enough that if you can understand it, you can it'll really help understanding these more complicated codes. And it's easy to install and get started with this one. So if you have a Python installed and pip, you can just run this command here in a terminal, and that should download and install FreeGS. And then this Jupyter notebook should work. I'm using FreeGS version 0.1.6. Hopefully anything later should work too. The code itself is on GitHub, so if you click on this link, it should take you to the page, and there's a manual available under this link as well. Okay, so just to recap, this is what it's doing. It's solving the Grach-Farnoff equation. So we have an equation on the right for the parallel current. This is J phi is parallel current, which is a function of r, major radius, and height. And this J is determined by the pressure gradient. So we have P, which is a function of poloidal flux psi, and F, which is major radius times toroidal field. And so these F and P are flux functions that we specify, and then this determines the toroidal current. But this depends on psi, and psi is determined by solving this equation on the left. So this is an elliptic equation, so it's a linear equation. Depending on J, we have a solution for psi in R and Z. And so this is a nonlinear partial differential equation. And so the way this code works is by iterating. So we start with a guess for psi. We use that. So we start with a guess for psi. We use that to calculate current, and then we resolve this equation to calculate another psi, and then keep iterating around a loop. Okay, so there are various components to this. So we'll use FreeGS, the library, and we'll use a boundary conditions. There are lots of options for boundary conditions. For now, we just want the fixed boundary. The first task is to set up the flux functions P, so the pressure, and F, and which then determine the current. There are many ways of doing this. The way that's used here is following this quite nice paper, which explains many of the details and from which most of this code was adapted. And so here we use a form of this equation, and you can see that here this is J phi from the Grach-Farnoff equation. And there is one component which is here proportional to major radius, and one component which is proportional to 1 over major radius. And this is what appears here. So here we have this component proportional to radius, which is the pressure component, and then this component over here, which is like 1 over radius, and this is from this F. And they are both functions of psi. So F prime and P prime are both functions of psi, and this is captured in this part here, this J tilde. And so now J tilde is a flux function we can choose, and it determines the shape of the current. And it looks like this. So it's a 1 minus normalized psi, so psi n is a normalized psi, and this is defined by this. So psi axis is on the magnetic axis, so in the core of the plasma, and psi boundary is at the edge. And so this psi normal goes from 0 on the axis to 1 on the boundary. And so J, the shape of the current, starts at 1 when psi n is 0, and goes down to 0 at the boundary. And depending on these coefficients, we can set alpha So alpha m and alpha n, these are coefficients we can set, and will change the shape of the current. And then there are two constants here. So one is this lambda and this beta, or beta naught. And these are set by two constraints. So we can choose two things to fix. One way is we can fix the maximum pressure, and we can fix the plasma current. So that gives us two constraints with two unknowns. The other way is to constrain the poloidal beta and the plasma current. So the poloidal beta is related to the plasma pressure. It's the ratio of plasma pressure to average poloidal magnetic pressure. And those two constraints are also enough to determine this lambda and this beta. Okay, in the code this is done. If you follow this link, it will show you the code where these constraints are calculated. When you want to use the code, you specify doing this. So it's in the FreeGS library. It's the toroidal current, and we constrain it using the pressure on the axis and magnetic field, and the plasma current IP. And this is the plasma pressure in pascals, so 1 kilopascal on axis, and 100 kiloamp plasma current. Then finally we just specify the toroidal magnetic field. So this is F in the vacuum, which is the major radius times toroidal field. And that's enough to constrain the profiles of F and P. Okay, so that's the profiles. Then we specify the grid that we want to solve on. So the domain we want to solve over the Grashofanov equation. So this is this part here. So we create an equilibrium object which is over some range of major radius. So it's advisable not to go too close to r equals 0, because there are various terms in the equations which depend on 1 over r. So here we have some small minor radius, and we start at 0.1 and it goes out to 2, and the same in height. So it goes from -1 meter to +1 meter. So these quantities are all in meters. This is the resolution, so the number of grid cells. It includes the points on the boundary, and for efficiency should be the power of 2 plus 1. So like this is 64 plus 1, so you can have 129, for example, or 33. And this is for two reasons. One is that we often want to integrate over the whole domain, and there's an efficient and accurate way of doing that called a Romberg integration, and that requires 2 to the k plus 1 points. For large grids, it's also quite efficient to use a multi-grid scheme where you have multiple levels of resolution, and if you have 2 to the k plus 1 points, this also becomes much easier. So this is one reason why you often see these kinds of resolutions. So 65 by 65 or 129 129, quite common in free boundary codes. So now we get to the main part. So we've specified the profiles and the shape of the grid, and now we want to actually do the solving. So there's several steps to this. So first we choose a guess for psi, and then we use this Picard iteration scheme. Now the main loop is in this link, if you follow this. The main steps are these. So we calculate the poloidal current, calculate the toroidal current using this object we defined. So that was the toroidal current in terms of from the pressure on the axis and toroidal field, toroidal currents. And then we specify the boundary conditions, and this is this fixed boundary for now. So that was here. So here we specify that the boundary should be a fixed boundary, and in practice that just means that it sets psi equals 0 on the outer boundary. Then we solve the elliptic operator. So we invert delta star to get the next solution for psi. And we check if if the difference is less than some tolerance. If it is, then we quit. We're finished. And then if it is still changing, we have to start the loop again. One optional step is to mix together these two solutions. So you can average these two and use that as the starting point for the next iteration. But usually that's not needed. And this whole iteration is started by calling this function here. So the solve is the Picard solve. EQ is this object we created up here. That was this EQ, which is the equilibrium object, which tells it what the grid points are, and contains the solution. And then profiles were the toroidal current, and so contains pressure and toroidal currents. Because then it goes through the iterations. So you see these are the parameters it's set in. This is lambda in the formula, and this is that beta naught. And so it goes through these iterations, each time updating. You see initially it's changing quite a large amount. And as the iterations go on, it fairly quickly reaches it stops changing so quickly. And saying the maximum change in psi also reduces, so from 10 to the minus 3 down to 10 to the minus 4, down to 10 to the minus 5. And this is set by the tolerance, so you can specify a smaller tolerance if needed. And then it will go for more iterations and converge further. Finally, we can plot. So there's a bunch of routines for plotting. Plot equilibrium is one of them. So this just takes the equilibrium object we've solved for and plots it. And here we have a domain. So this is going from 0.1 out to 2 meters is the range in major radius we asked for, and -1 to +1 in height. And these are contours of constant psi. Obviously there's just one O point is where the contours go around in a circle, and there's at the middle there's a point where the field line is purely toroidal. That's the O point. Okay, having got an equilibrium, we can then calculate some additional properties. So we can calculate things like the plasma current, and this will integrate over the domain. So it'll calculate J toroidal current density everywhere using the constraints that we specified, and then integrate them using the Romberg method and give back the current. And so this is a check, just a sanity check that we're getting back the current we asked for. So we specified 10 to the 5 amps, and indeed that's what it's given us. We can also calculate things like the poloidal beta or the pressure. So calculate the pressure, for example, as the equilibrium pressure, and then you specify the normalized psi. So on the axis, for example, indeed that gives us pressure in pascals, and this is the 1,000 pascals that we asked for. Okay, so we can try playing around with this a bit and modifying some things. So if you go back to the top and try, say, increasing the plasma pressure, so we increase this to say 5,000 pascals, you know, run it, you can specify the domain again, just go through each of these steps. Now when I run this, it should run through, it'll take a bit longer to solve this time, and then plots again. I can see that the equilibrium is now shifted to the outside, and this is the Shirvanov shift. So as the pressure is increased, the shift becomes larger and larger, and eventually it will stop converging, which corresponds to an equilibrium beta limit. So let's see if we can do that. Okay, higher pressure. See if we can break this. Yes, at this point the equilibrium has failed, and it's failed with an error message that it eventually can't find any O points. So essentially the plasma has hit the outer wall, and then it's completely diverged at this point. So the solution fails. And this is partly numerical, but this is also a physical effect, in that if your plasma beta is too high, the Shabanov shift becomes excessive, and you end up with either an X point on the inside or just no solution. So this is a beta limit just due to the equilibrium and outer shift. So you should be able to fix this by increasing the plasma pressure, the plasma current. So if you went to a higher plasma current, it should enable us to get to a higher pressure. And indeed, that's now has found a solution again. So this is useful just for playing around with what the limits are, so where the beta limits are, and you can compare this to the solutions you get from simple Soloviev equilibrium, and see where the beta limits are. Hopefully this algorithm is also useful for understanding more complicated codes. So I've linked here to each part of the code where the calculation is done, and so you can hopefully follow through the logic of what's being done here, and hopefully make sense of what the more complicated codes are doing.